just building up that intuition from every single task involved in putting together the data center, you start to immediately get a sense at the detailed scale and at the broad system scale of where the inefficiencies are. And so you can make it more and more and more efficient. Plus, you have the big hammer of being able to say, let's do it totally different.
Yeah,
and remove all possible blockers.
That's right.
Is there parallels in the NVIDIA Extreme Systems co-design approach that you see in the way Elon approaches systems engineering?
Well, first of all, co-design is a ultimate systems engineering problem.
Yeah.
And so we approach the work that we do from that principle. The other thing that we do, and this is a philosophy that a thought, a state of mind, I guess, a method that I started 30 years ago, and it's called the speed of light. The speed of light is not just about the speed. Speed of light is my shorthand for what's the limit of what physics can do. And so everything that we do is compared against the speed of light. Memory speed, math speed, power, cost, time, effort, number of people, manufacturing cycle time, and when you think about latency versus throughput, when you think about cost versus throughput, cost versus capacity, all of these things you test against the speed of light to achieve all of these different constraints separately. And then when you consider it together, you have to make compromises, because a system that achieves extremely low latency versus a system that achieves very high throughput are architected fundamentally differently. But you want to know what's the speed of light of a system that achieves high throughput, what's the speed of light of a system that achieves low latency. And then when you think about the total system, you could make trade-offs. And so I force everybody to think about what the first principles, the limits, the physical limits for everything before we do anything, and we test everything against that. And so that's a good frame of mind. I don't love the other methods, which is continuous improvement. The problem with continuous improvement, it first of all, you should engineer something from first principles at the speed, with speed of light thinking, limited only by physical limits and physics limits. And after that, of course, you would improve it over time. But I don't like going into a problem and somebody says, hey, it takes 74 days to do this today, right now. And we can do it for you in 72 days. I'd rather strip it all back to zero and say, first of all, explain to me why it's 74 days in the first place. And let's think about what's possible today. And if I were to build it completely from scratch, how long would it take? Oftentimes you'd be surprised, and might come to 6 days. Now the rest of the 6 days to 74 could be very well reasoned, and compromises, and cost reductions, and all kinds of different things. But at least you know what they are. And then now that you know that 6 days is possible, then the conversation from 74 to 6, surprisingly much more effective.
In such incredibly complex systems that you're working with, is simplicity sometimes a good heuristic to reach for? I mean, if I can just, the Vera Rubin pod that you announced is just incredible. We're talking about 7 chips, 7 chip types, 5 purpose-built rack types, 40 racks, 1.2 quadrillion transistors, nearly 20,000 NVIDIA dies, over 1,100 Rubin GPUs, 60 exaflops, 10 petabytes per second of scale bandwidth. That's all just one.
That's just one pod.
That's just one pod.
Yeah, that's just one pod.
I mean, so you have and then even the NVL72 rack alone is 1.3 million components, 1,300 chips, 4,000 pounds crammed into a single 19-inch wide rack.
And Lex, we'll probably kind of crank out about 200 of these pods a week, just to put in perspective.
The amount of different components, I suppose simplicity is impossible, but is that a metric that you kind of reach for in trying to design things?
The phrase that I use most often is we need things to be as complex as necessary, but as simple as possible. And so the question is all that complexity there necessary? And we ought to test for that. And we ought to challenge that. And then after that, everything else above it, is gratuitous.
But some of the most incredible semiconductor industry broadly, but what NVIDIA is doing, some of the greatest engineering in history. So these systems are just truly, truly marvels of engineering.
It is the most complex computer the world has ever made.
Yeah, the engineering teams, I mean,
Yeah.
I don't know, it's not a competition, but I don't know. If it was like an Olympics of engineering teams, I mean, TSMC does incredible engineering. Like I said, ASML at every scale, but NVIDIA is going to give them a run for their money.
Yeah.
Just incredible, incredible teams.
Gold medalists in every single sport, all assembled right here.
And have to work together
Yeah.
and report directly to you. This is wonderful. You've recently traveled to China. So it's interesting to ask you, China has been incredibly successful in building up its technology sector. What do you understand about how China is able to, over the past 10 years, build so many incredible world-class companies, world-class engineering teams, and just this technology ecosystem that produces so many incredible products?
A whole bunch of reasons. First of all, let's start with some facts. 50% of the world's AI researchers are Chinese, plus or minus. And they're mostly in China still. We have many of them here, but there's amazing researchers still in China. Their tech industry showed up at precisely the right time. At the time of the mobile cloud era, their way of contributing was software. And so this is a country's incredible science and math, really well-educated kids. Their tech industry was created during the era of software. They're very comfortable with modern software. China is not one giant economic country. It's got many provinces and cities with mayors all competing with each other. That's the reason why there's so many EV companies. That's the reason why there's so many AI companies. That's the reason why there's so many, every company you could imagine, they all create some of them. And as a result, they have insane competition internally. And, what remains is an incredible company. They also have a social culture where it's family first, friends second, and company third. And so the amount of conversation that goes back and forth between, they're essentially open source all the time. So the fact that they contribute more to open source is so sensible because they're probably, what are we protecting? My engineers, their brothers are in that company, their friends are in that company, and they're all schoolmates. The schoolmate concept. It's one schoolmate, your brother for life, and so they share knowledge very, very quickly. And so there's no sense keeping technology hidden. You might as well put it on open source. And so the open source community then amplifies, accelerates the innovation process. So you get this rapid, incredibly great talent, rapid innovation because of open source and just, the nature of friends, and insane competition among the company. What emerges is incredible stuff. And so this is the fastest innovating country in the world today. And this is something that has everything that I've just said is fundamental to just how the kids were grown, the fact that they have excellent education, the fact that parents want them to do well in school, the fact that their culture is that way. These are just the thing about their country. And they showed up at precisely the time when technology is going through that exponential.
Plus, culturally, it's pretty cool to be an engineer. It connects to all the components that you're mentioning.
It's a builder nation.
It's a builder nation.
Yeah, it's a builder nation. Our country's leaders, incredible, but they're mostly lawyers. Their country's leaders, and because they're trying to keep us safe, rule of law, governing, their country was built out of poverty. And so most of their leaders are incredible engineers, some of the brightest minds.
to take a small tangent, because you mentioned open source, I have to go to Perplexity here, who you have been a fan of a long time.
I love it. Yeah.
And thank you for releasing open source Nematron 3 Super, which you can also use inside Perplexity to look stuff up.
Yeah.
Which is 120 billion parameter open weight MOE model. What's your vision with open source? So you mentioned China with DeepSeek, with Minimax, with all these companies really pushing forward the open source AI movement, and NVIDIA is really leading the way in close to state-of-the-art open source LLMs. What's your vision there?
First, if we're going to be a great AI computing company, we have to understand how AI models are evolving.
Mhm.
One of the things that I love about Nematron 3 is it's not just a pure transformer model. It's transformer and SSMs. And we were early in developing the conditional GANs, progressive GANs, which led step by step to diffusion. And so the fact that we're doing basic research in model architecture and in different domains gives us visibility into what kind of computing systems would do a good job for future models. And so it is part of our extreme co-design strategy. Second, I think we rightfully recognize that on the one hand, we want world-class models as products, and they should be proprietary. On the other hand, we also want AI to diffuse into every industry and every country, every researcher, every student. And if everything's proprietary, it's hard to do research and it's hard to innovate on top of, around, with. And so open source is fundamentally necessary for many industries to join the AI revolution. NVIDIA has the scale and we have the motives to not only skills, scale, and motivation to build and continue to build these AI models for as long as we shall live. And so therefore we ought to do that. We can open up, we can activate every industry, every researcher, every country to be able to join the AI revolution. There's the third reason, which is to recognizing that AI is not just language. These AIs will likely use tools and models and subagents that were trained on other modalities of information. Maybe it's biology or chemistry or, laws of physics or, fluids and thermodynamics. And not all of it is in language structure. Mm-hmm. And so somebody has to go make sure that weather prediction, biology, AI for biology, physical AI, all of that stuff can be pushed to the limits and pushed to the frontier. We don't build cars, but we want to make sure every car company has access to great models. We don't discover drugs, but I want to make sure that Lilly has the world's best biology AI systems so that they can go use it for discovering drugs. And so these three fundamental reasons, both in recognizing that AI is not just language, that AI is really broad, that we want to engage everybody into the world of AI, and then also co-design of AI.
Well, I have to say, once again, thank you for open sourcing, really, truly open sourcing Nematron 3. And
yeah, I appreciate you for saying that. We open source the models, we open source the weights, we open source the data, we open source how we created it. Yeah, it's pretty amazing.
It's really incredible. You're originally from Taiwan and have a close relationship with TSMC. So I have to ask, TSMC, I think, also is a legendary company in terms of the engineering teams, in terms of the incredible engineering work that they do. What do you understand about TSMC culture and their approach that explains how they're able to achieve this singular, unmatched success in everything they're doing with semiconductors?
First of all, the deepest misunderstanding about TSMC is that their technology is all they have. That somehow they have a really great transistor, and if somebody shows up another transistor, game over. Mm-hmm. the technology, and of course, I don't mean just the transistor and metallization systems, the packaging, the 3D packaging, the silicon photonics, all of the technology that they have. That technology is really what makes the company special. Their technology makes the company special. But their ability to orchestrate the demands, the dynamic demands of hundreds of companies in the world as they're moving up, shifting out, increasing, decreasing, pushing out, pulling in, changing from customer to customer, wafer starting, wafer stopping, emergency wafer starts, all of this dynamics of the world's complexity as the world is shifting all the time. And somehow they're running a factory with high throughput, high yields, really great costs, excellent customer service. They take their work, they take their promises seriously. When your wafer, because they know that they're helping you run your company. When the wafers were promised to show up, the wafers show up, so that you could run your company appropriately. And so their manufacturing system is completely miraculous. I would say then the second thing is their culture. This culture is simultaneously technology focused on one hand, advancing technology, simultaneously customer service oriented on the other hand. A lot of companies are very customer service oriented, but they're not very technology excellent. They're not at the bleeding edge of technology. Or a lot of companies who are at the bleeding edge of technology, but they're not the best customer service oriented company. And so it just depends on somehow they've balanced these two, and they're world class at both. And then probably the third thing is the technology that I most value in them. That they created is, this intangible called trust. I trust them to put my company on top of them. That's a very big deal.
Well, they trust. I mean, there's a really close relationship there that you have established, and that trust is established based on many years of performance. But there's human relationships involved there as well.
3 decades. I don't know how many tens, hundreds of billions of dollars of business we've done through them, and we don't have a contract. That's pretty great.
Amazing. Okay, there's the story that in 2013, the founders of TSMC and Morris Chang offered you the chance to become TSMC's chief executive. And you said you already had a job. Is this story true?
Story is true. I didn't dismiss it.
Yeah.
But I was deeply honored, and of course, I knew then, as I know now, TSMC is one of the most consequential companies in history.
Yeah.
And Morris is one of the highest regarded executive and business and personal friend that I've had in my life. And for him to ask is I was humbled and really honored. But the work that I'm doing here is really important, and I've seen, in my mind, anyways, in my mind's eye, what NVIDIA was going to be and what the impact that we could have, and it was really important work, and it's my responsibility, my sole responsibility to make this happen, and so I declined it, not because it wasn't an incredible offer. It's an unbelievable offer, but I simply couldn't take it.
I think both NVIDIA and TSMC are two of the greatest companies in the history of human civilization. And running either one, I'm sure, is incredibly complicated effort, and you have to truly be all in.
Yeah.
Everybody at every scale, not just at the CEO level, everybody is really, truly all in.
Yeah.
No
doubt.
To accomplish this kind of complexity.
See, now I can help both companies.
Exactly. So NVIDIA is now the most valuable company in the world. I have to ask, what is NVIDIA's biggest moat, as the folks in the tech sector say?
Mm-hmm.
The edge you have that protects you from the competition.
Our single most important property as a company is the install base of our computing platform. Our single most important thing is today is the install base of CUDA. Now, the reason why 20 years ago, of course, there was no install base. But if somebody came up with a CUDA or TUDA, it wouldn't make any difference at all. And the reason for that is because it's never been just about the technology. The technology, of course, was incredible, visionary. But it's the fact that the company was dedicated to it, stuck with it, expanded its reach. It wasn't 3 people that made CUDA successful. It was 43,000 people that made CUDA successful. And the several million developers that believed in us, that trusted that we were going to continue to make CUDA 1, 2, 3, 13, that they decided to port and dedicate their software on top of it, their mountain of software on top of it. And so the install base is the number one most important advantage. That install base, when you amplify it with the velocity of our execution at the scale that we're talking about, no company in history had ever built systems of this complexity, period. And then to build it once a year is impossible. And that velocity combined with the install base in the developer's mind, you just can now take a developer's mind. From the developer's perspective, if I support CUDA, tomorrow it will be 10 times better. I just have to wait 6 months on average. Not only that, if I develop it on CUDA, I reach a few 100 million people, computers. I'm in every cloud. I'm in every computer company. I'm in every single industry. I'm in every single country. So if I create an open source package and I put it on CUDA first, I get these both attributes simultaneously. And not only that, I trust 100% that NVIDIA is going to keep CUDA around and maintain it and improve it and keep optimizing the libraries for as long as they shall live. You could take that to the bank, and that last part, trust. You put all that stuff together, if I were a developer today, I would target CUDA first. I would target CUDA most. And that's the reason that I think in the final analysis is our first, that's even our first core advantage. Our second one is our ecosystem. The fact that we vertically integrated this incredibly complex system, but we integrated horizontally into every single company's computers. We're in the Google Cloud, we're in Amazon, we're in Azure. We're ramping up AWS like crazy right now. We're in new companies like CoreWeave and Nscale. We're in supercomputers at Lilly. We're in enterprise computers. We're at the edge in radio base stations. It's just crazy. One architecture is in all these different systems. We're in cars, we're in robots, we're in satellites, we're out in space. And so the fact that you have this one architecture and the ecosystem is so broad, it basically covers every single industry in the world.
Well, how does the CUDA install base evolve into the future with AI factories as a moat? Do you think it's possible that NVIDIA of the future is all about the AI factory?
Well, the unit of computing used to be GPU to us. Then it became a computer. Then it became a cluster. Now it's an entire AI factory. When I see a computer, when I see what NVIDIA builds, in the old days, I visualize the chip. And then when I announced a new product, new generation, like, ladies and gentlemen, we're announcing Ampere today, I pick up the chip.
Yeah.
That was my mental model of what I was building. Today, I wouldn't, picking up the chip is kind of still adorable, but it's adorable. It's not my mental model of what I'm doing. My mental model is this giant gigawatt thing that has power generation, is connected to the grid, it's got cooling systems and networking of incredible monstrosity. 10,000 people are in there trying to install it, hundreds of networking engineers in there, thousands of engineers behind it trying to power it up. Powering up one of those factories, as you know, it's not somebody going, it's on now. It takes thousands of people to bring it up.
So mentally, you're actually, when you're thinking about a single unit of compute, you're like, literally, when you go to bed at night, you're thinking now about collection of racks, so pods, not individual chips.
Entire infrastructure. And I'm hoping my next click is, when I'm thinking about building computers, it's, planetary scale. That'll be the next click.
What do you think about the space angle that Elon has talked about doing compute in space for solving it makes some of the energy issues in terms of scaling energy easier?
Cooling issues is not easy. Yeah.
Cooling, well, there's a large number of engineering complexities involved with that.
Yeah.
So what, NVIDIA has also announced that you're already thinking about that.
Yeah, we're already there. NVIDIA GPUs are the first GPUs in space. And I didn't realize it was so interesting I would have declared it maybe. We're in space, little astronaut suit on one of our GPUs. But we've been in space. It's the right place to do a lot of imaging, because those satellites have really high resolution imaging systems, and they're sweeping the Earth, continuously now. And you want, centimeter scale, imaging that is done continuously for the world, so that you'll basically have real-time telemetry of everything. You don't want to beam that back down to Earth. It's just petabytes and petabytes of data. You got to just do AI right there at the edge. Throw away everything you don't need, you've seen before, didn't change, and then just keep the stuff that you need. And so AI ought to be done at the edge. Obviously, we have 24/7 solar if we put it at the polars, and but there's no conduction, no convection, and so you're pretty much just radiation. And but space is big. I guess we're just going to put big giant radiators out there.
How crazy of an idea do you think it is? Like, is this 5 years out, 10 years out, 20 years out? So we're talking about blockers for AI scaling.
I'm just so much more practical. I look for where my next bucket of opportunities are first. Meanwhile, I'm cultivating space, and so I send engineers to go work on the problem. We're learning a lot about it. How do we do with radiation? How do we do with degrading performance? How do we deal with continuous testing and attestation of defects, and how do we deal with redundancy, and how do we degrade gracefully and things like that? And so we could do what about software? How do you think about software and redundancy and performance out in space? Make it so that the computer never breaks; it just gets slower, and so we could start doing a lot of engineering exploration up front. But in the meantime, my favorite answer is eliminate waste. We've got all that idle power. I want to evacuate it as fast as possible.
Yeah, there's a lot of low-hanging fruit here on Earth that we can utilize for the AI scaling. Quick pause. Quick 30-second thank you to our sponsors. Check them out in the description. It really is the best way to support this podcast. Go to lexfridman.com/sponsors. We got Perplexity for curiosity-driven knowledge exploration, Shopify for selling stuff online, Element for electrolytes, Fin for customer service AI agents, and Quo for a phone system like calls, texts, contacts for your business. Choose wisely, my friends. And now, back to my conversation with Jensen Huang. Do you think NVIDIA may be worth 10 trillion at some point? Let's ask it this way. What does the future of the world look like where that's true?
I think that NVIDIA's growth is extremely likely, and in my mind, inevitable. And let me explain why. We're the largest computer company in history. That alone should beg the question, why?